Hi there, this is a quick lesson on angular momentum, and this video will cover the major topics, the major equations that are involved, and the concepts, and there's going to be a lot of similarities between angular momentum and linear momentum or translational momentum. This is the last part of this unit. Let's look at what we have. If you're working on this homework, here are the objectives, the last two objectives, and a set of problems going with the topic, angular momentum. Let's start with the angular momentum of a solid body. So here in my slide, I have an animation of a rotating object. So it could be anything. We have this blob-like object rotating. For an object rotating about a fixed axis, that object would have a moment of inertia, or rotational inertia I, and an angular velocity omega. And just like linear momentum is mass times velocity, angular momentum is rotational inertia times angular velocity. Our symbol is capital L. This would be a vector in the same direction as omega. So if the object is spinning counterclockwise in this animation, then our angular momentum would likewise be counterclockwise. Or as a vector by the right-hand rule, it would be sticking out of the page if you wanted to use that formulation for the vector. Definitely has a direction, right? Rotation has a direction, angular velocity has a direction, angular momentum has a direction. There is a concept called angular impulse. So all of this starts to sound kind of familiar. If we study momentum, we have momentum, impulse, etc. Well, similar quantities with rotation. Angular impulse is what you would expect. Impulse is the product of force and time. Angular impulse is the product of torque and time. So if a torque acts on an object for a period of time, that can be considered to be an angular impulse. And here's an equation. The integral of torque dt would give us a quantity that would be equivalent to angular impulse. Angular impulse is a quantity that might be useful to help us analyze a collision or an impact. See the video on the sweet spot for an example. Angular impulse should be equivalent to change in angular momentum. And a very similar and related concept, torque should be equal to the rate of change in angular momentum. So if we have a rotating body and it undergoes some sort of change in angular momentum, we can equate that with the product of torque and time, or angular impulse. And then torque causes angular momentum to change. Rate of change relates to rate of change in angular momentum is equatable with the net torque on a physical body or system. And really one of the main things that makes momentum useful, in my opinion, is that momentum is a conserved quantity, and that's also true for angular momentum. Angular momentum is conserved in an isolated system. Here you can see a description, like what do we mean when we say isolated? An isolated system would have no net external torque, but might have internal torques. So if two objects interact, they can exert torque on one another, and torque would follow a rule like Newton's third law. Torques occur in equal and opposite pairs. So if one object torques another, that object torques back with an equal and opposite amount, and that's going to cause an equal and opposite change in angular momentum. And that would mean that net total angular momentum of those two interacting objects should remain constant. So that's very similar to the way linear momentum is conserved. Internal torque is not going to change angular momentum, but it would move angular momentum around within a system. There is also, with angular momentum, a unique concept, the angular momentum of a particle. So I have an animation here which might strike you as odd, but let's just watch it. So I have my spinning blob again. Spin, Mr. Blob. And then going by the spinning blob, I have an object moving in a straight line. Now, we wouldn't normally think of that object moving in a straight line as spinning. But in a sense, it is spinning. If you think about it, it's going around the axis of rotation that the blob is spinning about. Let's watch it one more time and try to just see the connection. Like, even though it's moving in a straight line, if you wanted to, you could think of it as rotating about the axis shown at the origin of the coordinate system. So let's watch it one more time and just kind of get that visual in your mind. If it goes around the origin, we can assign an angular momentum value to it while it's going around. And that's an interesting little formula. It's also a handy little formula for certain types of problems. Let's draw a line out from the axis to our object. And as it moves along, that line changes. Even if the velocity is constant, r is changing. But while that's happening, we could determine the angular momentum of the particle by a formula L equals r cross p, where p is the linear momentum of the object moving along the line. The way I've got this illustrated, the angular momentum would actually be constant if it has a constant speed. The cross product r cross p would be the perpendicular distance from the line that's traveling upon to the axis, and that would end up being a constant. Even though r is changing, r cross p would be constant if p were constant in this animation. Quirky little formula, but it's a cross product, so it works, and as far as the calculation goes, very similar to finding a torque, except instead of force, we're doing r cross p, where p is momentum. Momentum can be found by mass times velocity in the normal way with this formula. Lowercase l is kind of a traditional symbol for this type of angular momentum, but it's equivalent to the angular momentum shown previously in this video. L equals I omega. I have a slide to show that. So let's talk about that. Where does that formula come from? Well, if we buy into the idea that L is equal to I omega, and we see the logic in that, well, what if we tried to apply L equals I omega to this object, this particle moving in a straight line? That particle, I'm going to activate my pointer here, that particle would have a certain velocity in the direction of its momentum. So notice I added a little velocity vector here. If I want to, I can draw some components on that velocity vector. And one of those components is perpendicular to r. And if we look at this diagram, I've got v perpendicular to r, I have omega. Instantaneously, omega would relate to those quantities. Omega would be that perpendicular velocity component divided by r. So in the formula L equals I omega, we can come up with an expression for omega that would be valid wherever the particle is along this line that it's moving. I would just be mr squared, rotational inertia of a point object, and that's what we're talking about, a particle-like object, point-like object. And now we have an expression for L, mr squared times v perpendicular divided by r. Well, of course, r would simplify. I can divide by r. And I also rearranged it. Notice I rearranged m times v perpendicular, and well, wait a minute, m times v perpendicular would be a perpendicular component of momentum. And if I think about that, well, the r in this diagram times a perpendicular component of that momentum vector would be equivalent to a cross product. And that's a very convenient way to write it, to say, well, whatever the quantities are, however you draw this picture, that would always be equal to R cross P. And then capital L, totally by tradition as far as I know, is usually written as a lowercase script or cursive L if we're talking about the angular momentum of a particle. Important to note that I can use the same ideas with this angular momentum that I can use with other types of angular momentum. So, for example, the net torque on a particle would be equivalent to the rate of change in the angular momentum of the particle given by this formula for finding the angular momentum of the particle. Or the angular impulse would equal the change in angular momentum. Conservation of angular momentum. I can use this type of angular momentum with the other type, the solid object rotating. So even though it's a slightly different symbol, that's just a matter of tradition, and it can still be equated. It's still angular momentum. Those are the key concepts for angular momentum. So have fun with it.